Hello friends, welcome to my channel. Let's have a look at problem 907, sum of subarray minimums. In this video, we are going to share a solution based on monotonic stack. We are going to explain the how and whys, and also explain some subtle points. First, I'll read through the problem statement to digest the problem requirement, and then we do the analysis, and finally we share the code. So first, the problem statement. Given an array of integers called array, find the sum of min b, where b ranges over every contiguous subarray of array. Since the answer may be very large, so we are required to return the answer in the sense of modulo this constant, that is 10 to the power 9 plus 7. So here are two examples. Actually, in my opinion, these two examples are not very representative. So in other words, they do not exhibit the generic case. So we'll explain why later. So in example 1, so the output is 17. So actually, here in the explanation, it lists all the possible subarrays and then do the find the minimums and do the summation. So similarly in example 2, because the length is only 5, you can do the listing and find the sum. So that's 444. So with that said, let's also look at the constraints. First, the array or the list is not empty, and its length is bounded above by 3 times 10 to the power 4. And also the elements in the array are bounded in between 1 and 3 times 10 to the power 4. So with that said, we are ready to do the analysis. First, so the method we are going to use is the monotonic stack. For some friends, it might sound complex for this method. Actually, it's very routine if we understand the hows and whys and some subtle details here. So here first I'm going to explain the idea, and then we give some walkthroughs, and then finally we share the code. So actually, once we understand the essence, then writing code in different formats is just a routine thing. Now let's look at the idea. So here the idea actually is very straightforward. So for each index I, we would like to find the number of subarrays that has this array I being the minimum. For this, actually we could do the computations for each index the following two quantities. The first quantity is how many elements j to the left, in other words j is less than or equal to I, such that array j is greater than or equal to array I. And each such index, let's call it j left, and can be used as a starting index for a subarray. So the second quantity we want to compute is how many elements j to the right, in other words j is greater than or equal to I, such that array j is greater than or equal to array I. And each such index j, let's call it j right, can be used as an ending index for a subarray. And then the problem becomes easy. So each subarray represented by the starting index j left and the ending index j right is a subarray with array I as or being the minimum. Then the total number of subarrays is just the n number of j left times number of j right. So therefore, the contribution of array I is nothing but the number of j left times the number of j rights. So then multiply by array I, right? So this is the overall idea. So actually, these two items is not very rigorous. So I'll explain why. So below. So first, let's give a walkthrough using example 1. So in example 1, so the array is 3, 1, 2, 4. Then I'm going to use left eye to denote how many elements at index I or to the left that are less than are no less than array I. So similarly, right eye means how many elements at index I or to the right that are no less than array I. So then if we use this example, so for 3, then to the left there is 1 element no less than 3. So we have 1 for 1. So to the left there are 2 elements no less than 1. So that is 3, 1. So we get 2 here. Similarly for 2, so to the left it's only itself, right? So we count to 1. So similarly for 4, this is 1. And then to the right for 3, so to the right is only 1 itself. For 1 there are 3, that is 1, 2, 4. So for 2 there are 2, that is 2 and 4. So we get 2 here. For 4 it's just itself, so we get 1. Then the result will be the number of subarrays. So it's just the corresponding product of the elements in left and right. That is 1 times 1, 2 times 3, and 1 times 2, and 1 times 1. Then we multiply the corresponding elements of the array, and then we do the modulation, right? So we modulo that big constant. So we get 17. So this is almost right. The reason is that, so in this, because this example is very special. So similarly, example 2 is also very special. The reason is that we need to avoid repetition in counting. So for example, for this example, so we get 255. So this example actually represents the generic case, right? Because one element can appear multi-times, right? Multi-times. So in this case, if we use the above reasoning, so the left will be, so for 71 it's just 1. For 55 it's 71 and 55, that is 2. For 82, so to the left it's only itself, so that is 1. So 55 there will be 4, right? All the left 3 including itself are no less than 55, so we get 4. And then for the right, so for 71, so we get 1. For 55 we get 3, this 2 to the right and itself. And for 82 we get 1. For 55 we get 1. Then if we sum the left eye times right eye times array eye, then do modulation, so we get 703. You can do the computation yourself. So this result or this return is not right. So here the subtle point lies in there are 2 55s. So actually we have repetition in counting. So this is easily seen, right? So for the first occurrence of 55, so let's look at the left and the right corresponding to this one. That is 2 and 3, right? So in other words, the subarrays can have starts, so 0, 1, right? So 0, 1, 0, 1 here. And also it can have end, so this one, so it's 1, this 1, 2, and 3. So we get stars, and there are 6 possibilities. That is 2 times 3. So if so this is one occurrence. Another occurrence, this one, right? We have left this 4 and the right is 1. So the left starts can be 0, 1, 2, 3, and end can be 3. And then if we compare this starts and end and this starts and end, so we found that, so we double count the subarray starting at index 0 and 1 and ending at 3. In other words, so the start of the intersection of this start and this start, right? So the intersection is 0, 1. So this intersection for the two ends actually are 3. So we have repetition, that the repetition number is 2 times 1. 2 is the number of elements in the intersection of the two starts, and 1 is the intersection, the number of elements in the intersection of the two ends, right? So this is a problem. So actually for this problem, it can be easily treated. So here is the treatment. So we just need to make a strict inequality, strict. For using this one, array J is strictly larger than array I in one and only one set. So if we do this array J strictly larger than array I, when we compute the left I, so we will get this one, left 1 2 1 2. So right remains unchanged. So here, originally it's 4, so now we get 2. So we eliminate the repetition. Or we can do the same thing, but we use strict inequality on the right counts. So if we use strict inequality in the right counts, so the left will not change. It's 1 2 1 4, and then the right will become 1 2 1 1. So originally it's 3, and then here is 1. So 2 times 2 is 4. Originally 2 times 3 is 6. So we eliminate the 2 repetitions, right? So with that said, I guess we know the hows and whys and the subtle points. So overall, the idea is like this. So for each index, we count how many elements to the left of I, which is no less than the array I, and how many elements to the right, which are no less than the array I. So both cases, we include the array I itself. And then, so we do the multiplication. So this will be the contribution times of array I being minimum. So as we do the walkthrough, we notice that we need to use a strict inequality in one of the two sides when we do the counting. So with that said, so we are ready to write the code. Actually, once we realize the overall idea and the subtle points, so writing the code is very straightforward. However, there are some points I want to demonstrate. So with that said, let's do the coding. First, let me write this length n array. So I'm going to introduce this variable n just for convenience. So this is not essential, right? So first, I'm going to compute this. So for each index I, we want to find how many elements with index less than or equal to I, such that are no less than array I, right? So this is actually a very typical task. So we just need to, for this, we use monotonic stack. So let's write this using this stack. So I'm going to introduce this list empty, and then I'm going to call this left. So in other words, for each index, I'm going to get left I, which is the number of elements to the left, and include the number itself that are no less than array I. So this is very simple because we need to do an iteration in the forward fashion, that is for I in range m, right? So for this, I'm going to do a very standard monotonic stack, while stack, in other words, if the stack is not empty, and stack -1. So this is the top element in the stack. If this corresponds to an element which is no less than the array I, so let me write array I, and then we're going to do stack pop, right? So after this while loop, there are two possibilities. First, the stack is empty, or the stack is not empty, but this condition is validated. Then for this, let's consider the two cases. First, if not stack. So in this case, so the stack is empty. It means that all the elements to the left of the current index is no less than array I. So in this case, so we are going to have left I equals I plus 1. So the plus 1 means we include the array I itself. So this is the one case. Another case is that stack is not empty, and this condition is validated. So this stack top element will be corresponding to a number less than array I. So then actually the left I, the number of elements less than or equal to array I and including array I is nothing but I minus stack -1. So this way, so we finish the main logic. So at the very beginning, stack is empty, right? So we need to add this one. So this is important. Don't forget that. So this way, we finished determining the left, right? So similarly, we want to determine the right. So let me write some comment. So for each index, so let me copy this part. So let's put it 2. For each index, we want to find how many is greater than or equal to I, that are no less than array I. So for this, we use monotonic stack. So here are 2 choices. So first, so you can reverse array, right, and use the above code, right. So this is the version 1, choice 1. Second choice, so we write directly. So but reverse using backward direction. So here I'm going to write directly just to practice, right? So for this, I'm going to initialize a stack just parallel to above, but the direction is different. So I'm going to initialize a right to be 0 times m, right? And then we're going to do the iteration. So for I in range, so n minus 1, -1, -1, right? And then what we're going to do is again the monotonic stack condition. While stack and array, the stack top, that is stack -1, is greater than or equal to array I. So in this case, what we're going to do, so we're going to do the pop, right? Again, after this while loop, there are 2 cases. First, stack is empty, or stack is not empty, and this condition is validated. So let's consider 2 cases. First, if not stack, in other words, stack is empty. It means that all the elements to the right of index I and including I are no less than array I. So in this case, we're going to set right I to be n minus 1, that's the end index, so minus the current index, then plus 1. So plus 1 means including the current array I. So this is the one case. So another case is that the stack is not empty, and this condition is validated. In other words, stack -1 corresponds to the index, which corresponds to an element begins to be smaller than array I. So in this case, so the right I is nothing but stack -1. So it should be -1, then minus the current index, and then include the current index. So if you simplify, this is nothing but stack -1 minus I. So here you can write n minus I, right? So let's, but it loses some meaning. So let's keep this n minus 1 minus I and plus 1, and this is stack -1 minus I plus 1, right? So do not forget to append this index I. So this way we finished computing the right array or list. So next we actually just prepare the return, right? Prepare the return. So for this, I'm going to do this. So let's initialize a result variable, and then we iterate for I in range m, right? So what we're going to do is that we do this, right? So the left I times right I, then multiply by array I, and finally we are going to return result in the sense of modulo this number 10 to the power 9 plus 7. So this forms a partially correct solution. The reason is that, so either when we computing the left or when we compute the right, we need to use strict inequality, one in one and only one. So you can use strict inequality here or here. So let me first use strict inequality in the left, right? So now let's do a check. Yeah, it passes this subtle case. For sure, it can pass this one, right? Let me copy this one and do a test. Yeah, it passes the example 1. Now let's look at the generic case. Yeah, it passes all the generic cases. Now let's change this one to be greater than or equal to, and then when we compute the right, we use strict inequality. And then let's do the check. Yeah, it passes the first example. So now let's check this example, right? So we're going to use this one. So this example, actually, as we mentioned in the previous in the beginning, it demonstrates the generic case. Yeah, it also passes this example. So now let's look at generic case. Yeah, it passes all the generic cases. But if you try to use both greater than or equal to in the 2, so you will get wrong through. You cannot pass all the test cases, in particular this one. So with that said, I guess that's about it for this specific problem. So in this video, we explained how to use monotonic stack and the hows and the whys and the subtle points in this problem. So as we commented, so here we write twice the code in order to fix the idea or practice, because we can write the monotonic stack in a forward fashion or in a backward fashion. This is good. Or you can write a hyperfunction and then call that function twice. But just notice that when you call the right, you just need to reverse the array. But reversing the array takes some extra time. So with that said, that's about it for this video. So actually we have a playlist for the applications of monotonic stack. So you are welcome to check out and compare with this specific problem. So with that said, I guess that's about it for this video. Thank you.